Hey, I'm Stan, and in this video, I'm going to talk about some basic image quality metrics in radiology. In this video, we'll first cover some background, and then a bit about noise and statistics, the resolution and system response, efficiency and noise analysis, as well as contrast and detectability. Understanding noise and statistical variability is fundamental to analyzing image quality, which in turn can improve diagnostic capability. The image quality depends on many factors, including the object or subject being imaged, the physical processes that are governed by statistics, as well as the imaging system in use. Noise refers to unwanted or random variations in the signal that degrade the quality of an image, potentially obscuring the visualization of structures or details within the scanned regions. Noise can come from electronic, quantum, and environmental sources. The image on the right is an axial CT slice of our cat phantom. This region of the phantom was designed and built to be uniform. However, we can see from this image that there is noise. The pixels are not all of the same value or brightness. There is variation due to noise. This noise is the combined effect from all the sources, including electronic, quantum, structural, and environmental. Image noise can be defined as the standard deviation of pixel intensity values in a uniform region of an image. Mathematically, that is given by the square root of the average square difference between each pixel value and the mean pixel intensity within that region. Now, we've seen the visual appearance of noise and how we measure it in an image, but how do we mitigate it? So quantum mottle can be mitigated by increasing the number of photons detected. So for example, increasing the MAS in CT or X-ray imaging, or using longer acquisition times in MRI. Alternatively, we can employ image processing techniques such as iterative reconstruction and noise reduction filters. Structural noise can be mitigated through regular quality control and detector calibration, digital image processing techniques, and an optimal selection of imaging parameters. Electronic noise can be mitigated by using low noise electronics, cooling electronic components to reduce thermal noise in the case of MRI, for example, and using signal averaging techniques or post-processing algorithms. Now, since quantum mottle is the dominant source of noise in medical imaging, we'll discuss that in a bit more detail. So quantum mottle is a specific type of noise that occurs due to the statistical nature of photon interactions during the image acquisition process. These interactions occur at a spatial scale where quantum effects take place. Quantum mottle is more prominent in low-dose imaging as it's related to photon counts. You can see on the graph here that interactions of photons with tissue are probabilistic events that depend on energy as well as the scattering angle. Counting statistics refers to the statistical variability inherent in processes where discrete events, such as the detection of photons, are counted over a period of time and within a region of interest. In medical imaging, this is highly relevant as the formation of a diagnostic image depends on optimizing sufficient counting statistics to achieve a good balance between radiation dose and image quality. If you consider the images on the right that show a photomultiplier tube and sodium iodide scintillator crystal detector setup, clearly a source with a higher activity, as shown below, is more likely to result in a photon interaction in the crystal and thus measuring a decay event. The Poisson distribution is a discrete probability distribution that describes the likelihood of a given number of events occurring within a fixed interval of time or space, provided the events occur independently and at a constant average rate. This distribution is ubiquitous in physics and is a very important one. Looking at the graphs on the right, these Poisson distributions are plotted based on generating random samples. The way the distribution takes shape for much higher number of sampling also demonstrates the importance of counting statistics. Signal-to-noise ratio, or SNR, is a quantitative measure that compares the level of desired signal to the level of noise. You can see a Scout MR image of the brain on the left and a T2 weighted image of the brain on the right. The second image will have a better signal-to-noise ratio for a given anatomical region. Decreased quantum mottle results in an increased SNR. In turn, this results in improved image quality through improved image contrast detection. SNR is more effectively improved with a higher signal. Since the standard deviation, or noise, is proportional to the square root of the mean, the signal-to-noise ratio is also proportional to the square root of the mean. Spatial resolution is the ability of an imaging system to display two adjacent objects as discrete entities. The spatial resolution will determine the ability of a system to distinguish small structures in the scanned region, which has important implications for diagnostic capability. So, for example, a higher resolution could allow for the detection of smaller lesions. And to measure spatial resolution, we use this concept known as line pairs, as shown in the diagram. As an example, you can see on the left the phantom for mammography, which shows line pairs. The number of line pairs per distance that you can visually distinguish and count reflects the spatial resolution of that system. Now, the mammography systems are required to have exquisite resolution, as very small pathology must be visible in tomograms. As another example, you can see on the left the phantom for fluoroscopy, and on the right an image of that phantom. Again, this shows the line pairs on fluoroscopic X-ray imaging, allowing us to determine the resolution of our system. The point spread function, or PSF, describes how an imaging system responds to a single point source object. It's related to the imaging system's spatial resolution, as the spread or blurring of the known point in the resulting image yields information about the system's capabilities. Now, if we let h of xyz represent the PSF in a 3D coordinate system, which is described in the first function, where capital H is the imaging system operator and delta of xyz is the Dirac delta function, representing an ideal point source. Then the line spread function, or LSF, is a 1D representation of an imaging system's response to a narrow line source, which is essentially the cross-sectional profile of the PSF along a specific axis. Illustrated here is the concept of a PSF, where you can see that this function in the middle, which is a Gaussian convolution, will cause an image to capture the shape of an object, but with blurring introduced. And in this diagram is the equivalent for a line spread function, where again the Gaussian convolution will cause the finite line source to be pictured but with a blurring introduced. These two examples demonstrate how the PSF is related to the resolution of a system. If we recall that resolution is related to the smallest adjacent objects that can be distinguished within the imaging system, then in the first scenario for this PSF, the two distinct objects being imaged can be distinguished. However, in the below example where the Gaussian convolution has a higher standard deviation, the images show that the two distinct objects cannot be distinguished. So imagine this is the difference between a bone and a lesion. In the second case, you would not be able to distinguish those two objects, which has implications for diagnostic capabilities. The modulation transfer function, or MTF, is a mathematical function that quantifies the ability of an imaging system to preserve contrast at different spatial frequencies. Essentially, it describes how well an imaging system reproduces detail of varying sizes from the object being imaged into the final image. The MTF is the magnitude of the normalized Fourier transform of the PSF. as described in this equation, where h of x and y is the PSF of the imaging system, f is the Fourier transform, u and v are the spatial frequency coordinates, and f of h x y at 0 is the direct current or zero frequency component of the Fourier transform, which represents the average signal response across the range of frequencies. The MTF ranges from 1 to 0, where 1 across all frequencies corresponds to perfect contrast, and 0 across all frequencies corresponds to no contrast at all. The MTF is highly relevant in medical imaging as it describes how effectively a detector can reproduce fine details of structures. A high MTF means that a system can accurately reproduce small features, whereas a low MTF indicates blurring or loss of fine detail. In the example shown here, the cast image is AI generated through a model called CycleGAN, while the no-cast image is just the original X-ray. A plot of the MTF indicates that the AI-generated cast image has a lower MTF at the higher spatial frequencies, which shows that the application of this CycleGAN model introduces an effective loss of resolution. And it's important to remember that loss of resolution can result in misdiagnosis, and in the case of wrist radiographs could be the misdiagnosis of a fracture. Detective quantum efficiency, or DQE, is a measure of the efficiency of an imaging system in converting the input signal, such as X-rays, into a useful output image while maintaining the quality of the information. This measure evaluates how effectively a system captures and preserves the contrast and detail from the input while minimizing the impact of noise, which mathematically DQE is defined as the squared output signal to noise ratio over the squared input signal to noise ratio. And in this case, f is the spatial frequency, which could be cycles per millimeter or line pairs per millimeter. The SNR in is the SNR at the input, which could be photon flux. And SNR out is the SNR at the output, which could be just the image. DQE values range from 0 to 1, where a higher DQE indicates better system performance with less noise added during signal conversion. DQE typically decreases as spatial frequency increases, reflecting the reduced efficiency in preserving fine details due to noise and system limitations, as shown in the diagram on the right. Higher DQE equipment will improve diagnostic capabilities, for example, by improving the detection of small or low contrast lesions. So the noise power spectrum, or NPS, is a quantitative description of the spatial distribution and frequency content of noise in an imaging system. It characterizes how noise varies across different spatial frequencies and provides insight into the texture and structure of noise in an image. So for a 2D imaging system, the NPS at spatial frequencies u and v are given by the below equation, which is related to the Fourier transform of the noise signal in the spatial domain. So a low power in the NPS indicates smoother, less noisy images, whereas a high power at high frequencies signifies grain or speckled noise. The NPS is a valuable tool for objectively evaluating image noise and system performance in medical imaging. These plots demonstrate how noise characteristics influence image quality and their corresponding frequency domain representations. So NPS is related to diagnostic capability. If we look at the two images, we can think, in which image would it be harder to detect a tiny bright lesion? Clearly, this would be harder in the below image with high noise or a high power NPS. So now moving on to contrast, we'll first talk about subject contrast, which refers to the inherent difference in the attenuation, reflection, or emission of energy between two adjacent tissues or regions in the body. It is the primary source of contrast in an image as it reflects the physical and biological properties of the tissues being imaged. And here we have the equation for subject contrast defined, which is related to the absolute difference between the intensities of the corresponding two tissues or regions. The tissue properties, imaging modality, spectrum of the imaging beam, tissue thickness, and pathology will all affect subject contrast. Image contrast is the difference in brightness or intensity between two regions or objects in a medical image. It determines how two structures can be visually distinguished from each other in the final image. Image contrast is determined by the inherent subject contrast, but also the imaging system's ability to capture and display that contrast. Image contrast is related to the absolute difference in the pixel intensities or brightness values of two adjacent regions in the image. Contrast detectability refers to the ability of an imaging system and the observer to discern differences in contrast between two adjacent regions or structures in an image. Essentially, it measures how effectively subtle variations in contrast can be detected amidst the noise and other factors that influence image quality. The minimum contrast difference that can effectively be distinguished by the imaging system and observer is often quantified as the contrast to noise ratio, which is defined here as the absolute difference in intensities of the adjacent regions divided by the noise. In the example of the CAT fan module, the CNR is related to the number of distinct circles that you can see, and this determines diagnostic capability. The more circles we can distinguish, the better chance we have of detecting lesions. So, as a result of photon-electron interactions, Compton scattered photons are redirected on a trajectory misaligned to the primary beam. So scattered radiation degrades contrast within an image by dispersing the photons over the image receptor, which generates pixel values which don't represent the level of absorption the primary beam has undergone. So a scatter correction algorithm, or SCA, as shown in the figure, can improve image quality in portable chest x-rays. So scatter degrades contrast and therefore image quality. So some of the key takeaways for this introduction to image quality metrics are that noise, especially quantum mottle, obscure fine details in diagnostic images. Statistical variability, or counting statistics, impacts image quality and follows mathematical distributions. Spatial resolution determines the ability to distinguish small structures. The point spread function, line spread function, and modulation transfer functions describe system response and detail preservation. Detective quantum efficiency measures a system's efficiency in converting input signals into high-quality images. The noise power spectrum describes the spatial frequency content and texture of noise in the image. Subject contrast arises from tissue properties like attenuation or emission differences. Image contrast and detectability depend on system performance and metrics like contrast to noise ratio. Some final key takeaways are that noise, contrast, and resolution are fundamentally properties that affect image quality. Low noise, high contrast, and high resolution improve diagnostic accuracy. The modulation transfer function, noise power spectrum, and detective quantum efficiency describe system performance. These do not act independently, so changing one can affect the other. So there are trade-offs in image quality. Increasing resolution can increase noise, and reducing noise can improve contrast, but excessive radiation dose is also problematic. So, in clinical practice, it's about optimizing all of these things to obtain a good diagnostic quality image with a minimum amount of radiation dose. That finishes the introduction to image quality metrics. Please get in touch if you have any questions or feedback. Thank you for listening.